Scene script. Have you ever pondered the fascinating question, what if everything around you, including you, was made of antimatter instead of matter? Today we're diving headfirst into the intriguing universe of matter and antimatter. Let's start with the basics. Matter, as we all know, is anything that has mass and occupies space. It's what makes up the earth beneath our feet, the air we breathe, and yes, even ourselves. But what about antimatter? Antimatter, as its name suggests, is the opposite of matter. It sounds like something out of science fiction, but it's very much a part of our scientific reality. Antimatter is composed of antiparticles, which, though they share the same mass with their matter counterparts, carry an opposite charge. For instance, an electron, a particle of matter, carries a negative charge. Its antimatter equivalent, the positron, carries a positive charge. This universe we inhabit, as far as we know, is predominantly composed of matter. It's in the stars that light up the night sky, the planets that orbit them, and the galaxies that these star systems form. But here's the thing, at the birth of the universe, the Big Bang, both matter and antimatter were created in equal amounts, or so we believe. Yet when we look around, we see a universe filled with matter, while antimatter seems to be the exception rather than the rule. It's one of the biggest mysteries in physics today. Where did all the antimatter go? And why is there an asymmetry between matter and antimatter in our universe? These are the questions that scientists are grappling with as they delve deeper into the world of particle physics. It's a challenging puzzle, but one that could fundamentally change our understanding of the universe and our place in it. So we dwell in a universe predominantly composed of matter, but what if it was antimatter instead? Join us as we continue to explore this thought-provoking question, diving into the science behind matter and antimatter, the asymmetry of the universe, and the quest for answers in this cosmic mystery. To understand the implications of our question, let's delve into the science behind matter and antimatter. Everything in the universe, from the smallest particle to the largest galaxy, is made up of matter. But did you know there's a mirror image of matter? An almost identical twin, if you will, but with an opposite charge? This is known as antimatter. The concept of antimatter first came to light in 1933 when physicist Paul Dirac proposed the existence of particles that have the same mass but opposite charge compared to matter. This theory was later confirmed with the discovery of the positron, the antimatter counterpart of the electron. Now here's the fascinating part. When a particle of matter meets its antimatter counterpart, they annihilate each other. This annihilation results in the release of energy. In fact, the energy produced is so immense that it's the most efficient energy release process known to physics. This principle is not just theoretical, it has practical applications in our day-to-day life. For instance, consider positron emission tomography, or PET scans, a common diagnostic tool in medicine. In a PET scan, a small amount of radioactive material is injected into the body. This material emits positrons, and when these positrons meet electrons in the body, they annihilate, producing energy in the form of gamma rays. These gamma rays are then detected and used to create detailed images of the body's interior. The existence of antimatter presents a tantalizing question. If matter and antimatter are mirror images, shouldn't there be an equal amount of both in the universe? Yet, everything we see around us, from the earth beneath our feet to the farthest stars in the sky, is made of matter. It seems the universe prefers matter over antimatter, but why is that so? This brings us to one of the greatest mysteries of physics, the matter-antimatter asymmetry. In the realm of physics, symmetry is a fundamental concept. When we talk about symmetry, we mean that a system remains unchanged even when it is transformed in certain ways. This is true for matter and antimatter. You see, every particle of matter has a corresponding antimatter counterpart that's virtually identical in every way, except it carries an opposite charge. An electron's counterpart, for instance, is the positron, which carries a positive charge. Now let's take a trip back in time, around 14 billion years, to the Big Bang. According to the theory, the universe began from a hot, dense state, and as it cooled, particles began to form. It is here where the concept of symmetry suggests that for every particle of matter, an equivalent particle of antimatter should have been produced. But here's the conundrum. If there were equal amounts of matter and antimatter, they should have annihilated each other completely, leaving behind only energy. And yet, here we are, in a universe filled with galaxies, stars, planets, and us. Somehow matter won out. This discrepancy between the expected symmetry and the observed asymmetry is what physicists refer to as the matter-antimatter asymmetry problem. It's one of the biggest unanswered questions in cosmology, a puzzle that scientists around the globe are trying to solve. Various theories have been proposed to explain this imbalance. Some suggest slight differences in the behavior of matter and antimatter particles. Others propose that there may be regions of the universe where antimatter dominates. Yet these theories remain unproven, and the evidence we've gathered so far seems to favor a universe of matter. So, the mystery remains: why does our universe favor matter? This question continues to challenge our understanding of the universe, pushing the boundaries of our knowledge and driving the quest for answers in the fascinating field of particle physics. Scientists across the globe are on a quest to solve this intriguing puzzle. The puzzle? Why does matter dominate our universe when theory suggests there should be an equal amount of antimatter? Let's take a trip to the European Organization for Nuclear Research, or CERN. Here, a 17-mile-long ring known as the Large Hadron Collider, the world's largest and most powerful particle accelerator, lies beneath the border between France and Switzerland. It's in this subterranean cavern that physicists are probing the deep structure of our universe. One of the key experiments here is the ALPHA experiment, which aims to trap antimatter atoms to study their properties. In 2021, ALPHA made a landmark achievement by measuring the spectral lines of anti-hydrogen for the first time. This experiment is a crucial step towards understanding why our universe is composed mostly of matter. At the same time, the LHCb experiment is investigating the minute differences between matter and antimatter particles. By smashing particles together at near light speed, scientists can create brief flashes of energy that momentarily become matter and antimatter pairs. This allows them to study these elusive particles before they annihilate each other. These aren't just academic exercises. Understanding why matter dominates our universe is crucial to our understanding of the fundamental laws of nature. It could reshape our grasp of everything from the Big Bang to the fate of the universe. But let's not forget, science is a process of discovery, and every answer brings new questions. As we peel back the layers of the universe, we're constantly surprised by what we find. The mystery of matter and antimatter is just another chapter in our ongoing journey to understand the cosmos. Remember, every discovery, every experiment, every question asked and answered brings us one step closer to understanding the nature of our universe. The quest for understanding matter and antimatter continues, and with it, our understanding of the universe evolves. Scene script. Let's return to our initial question: what if everything was made of antimatter instead? A fascinating proposition, isn't it? Imagine a universe where the tables have turned, where antimatter rules and matter is the outcast. This wouldn't be a mirrored universe with evil twins, but rather a parallel existence that would seem entirely normal to an observer within it. Why? Because antimatter behaves just like its matter counterpart. In this hypothetical antimatter universe, electrons would be replaced by positrons, protons by antiprotons. The laws of physics would still hold true. Gravity would pull things downwards, light would travel at the same breathtaking speed, and apples would still fall from trees. To an observer in this universe, everything would appear as we know it today. However, there's a catch. If we, beings of matter, were to somehow visit this antimatter universe, the meeting would be less than pleasant. The result would be mutual annihilation, a release of energy in accordance with Einstein's famous equation, E equals mc squared. But let's take a step back. The real conundrum isn't what an antimatter universe would look like, it's why our universe is one of matter, not antimatter. The Big Bang should have created equal amounts of both, so where is all the antimatter? This is one of the biggest unsolved mysteries in physics. In fact, the absence of detectable antimatter in our universe is so puzzling that it's called the baryon asymmetry problem. Theories abound, from slight differences in the decay rates of matter and antimatter to the possibility of hidden antimatter galaxies. However, none have been conclusively proven. In the grand tapestry of the cosmos, matter and antimatter remain two of its most intriguing threads. As we unravel these mysteries, we uncover the very fabric of our...
Please do like, share and subscribe to my channel. Thanks for watching.